Welcome to an explanation of a high-throughput train station. As background for this, I thought it would be cool to have a central station in a factory that basically every item would go through. So have like a central, some kind of storage array, just a whole bunch of chests lined up. And the next to that basically have everything you could possibly need gets trained into this, gets unloaded from the trains, stored, and then as it's needed, trains will be able to come in, have whatever they need, whatever like somewhere else in the factory needs, loaded onto it, and then the train can go off to the exact part of the factory. In order for this to be viable as sort of like actually everything in a factory goes through it, and as it goes through like different parts, different steps of building stuff, potentially stuff could come back like multiple times, right? So one of the main questions with this is sort of how do you load multiple different types of things onto a train and have that be able to be set by circuits. And this is an attempt at sort of the loading a train. So there's loading a train. You want it to be really fast, right? You want all the inserters to be going as fast as they possibly can. But also you want them to load exactly what you need. And it doesn't matter, it shouldn't matter what's in which of the chests around. So I want to load exactly what's needed to this train. The train would pull in and stop here. And I want to load exactly what's in these chests onto the train using these inserters. The problem, of course, is that you could have other stuff in the chest. So the idea is that when one train pulls in, the next train, so we got a train stop here, and then the next train could be sort of lined up behind it, ready to go. So you have this queue of trains ready to be loaded, right? We're talking like there could be multiple of these loading trains, but I just think it would be super interesting to have like a single crazy high throughput train, crazy high throughput loading station. And just have like many trains going through that, and it just like loading stuff as fast as possible, as fast as the trains can get to it. So we want to be able to load exactly what's needed onto many trains, queue up the items for the next train, which means that you might have items that aren't necessarily for this train, but are for some other train. Some other destination in these same chests, or like just sort of a chest away, 2 chests away, ready to go. I'm going to sort of talk through each piece of this and why each piece was necessary. So this will probably be a longer video, and so be it. Yeah. I guess that's the end of the introduction. Next up, let's switch to the loading things on. So a single inserter going from some container to some container, so either from a chest to a chest or from a chest onto the train. Moves items at approximately 30 items a second, if I recall correctly. But from a belt into a chest is roughly half of that. This is, of course, in the ideal case where what it's picking up is all the same. But if you have a small amount of like other items, there isn't really a way around that. So in the ideal case, if you're just like moving, like we need a bunch of X, this will operate relatively efficiently. So the idea here is you kind of have everything you need for the current train that's being loaded and the next train that's being loaded in the first chests, right? So you only load things onto the train that the train actually needs, right? But the one before that, so any of these, and obviously I haven't wired this up, but in theory, any of these, you would want to move what either this train needs or the next train needs. And then this one would be either what this train needs or the next train needs or the next train after that needs. So you have a few layers of sort of like stuff ready to go. And, if the current train needs something, you move it forward. And you only want to move forward into the next slot, like the amount that's needed. So you take what this train needs plus what the next train needs. That's what should be loaded into this chest, right? That's what should be moved over. That logic isn't done here, but it's relatively straightforward to do that, right? And if it isn't perfect, for most of these, it's fine, right? If you move a few too many iron plates, like whatever, the next train's going to pull in. Those are going to be loaded. It'll move on. Like it doesn't matter, right? In order for this not to get blocked, somewhere further upstream, there will have to be like a perfect amount, like load exactly this amount of whatever. There'll have to be some logic for that sort of before whatever that storage grid is. But for these, at least, it doesn't matter. However, for actually loading onto the current train, having the perfect, loading the exact amount you need is important. And that makes things significantly more complicated, as you can see by all of this circuit logic. I don't know if someone's done this before. I should clarify that. I don't know if someone's done this before. I've kind of designed this myself and intentionally did not go to see what there was. I wanted to put it together myself, see what could be done. So there's very likely already like blueprints for this and whatever, but this is the one I made, so be it. So the main thing, the thing we're really trying to do is load from these chests, right? These ones, using these inserters, filter inserters, into the train that is currently there. And we want to load exactly the amount that's defined in this circuit in here. So right now it's trying to load 12 gears. Right. So for just a quick demonstration, if we have some gears, we have, let's say there's 5 gears here, and 10 gears in the next one. And we're just going to put some arbitrary number in the next one. Okay, so 5, 10, 25. Okay, and the number we want is 12. Okay. So when this train rolls in, we want it to load exactly 12. Is this reset? Reset this. This is simply a counter of how much has been loaded already. So exactly 12 get loaded. Let's do a quick demonstration of a larger number. We'll back up this train. So exactly 12 got loaded. That's what we wanted. Now, you can see here, this is the number that was loaded. It's negative, but negative 12. 12, easy enough. And I'll reset that, and the amount we want has been set now to 0. So I'm gonna change this to say we want 100, let's make it 101, just to be a more difficult number. We want 101 iron plates, and we're going to just kind of spread these out. We'll put, I don't know, 5 here. 5, 7, 34, 100 down here. I don't know, 50 here. Let's put 50. Yeah. So we definitely have over 100 here. Not much over 100, but enough over 100. And we want exactly 101. So we want to fill this up with exactly 101. There's exactly 101 in it, as you can see over here. Obviously, I can't point at that while my mouse is over there, but 101. And the number we think we loaded is 101, and we don't need any more. Once again, turn the train off, back it up, 101. Yeah. So that's in essence what it does. And I probably should have demonstrated loading multiple types of items, but I'll leave that for the end. Okay, so let's talk about this crazy circuitry that's going on, and sort of go through it bit by bit. First of all, just starting here of what's obvious. Each chest has a line connected to it, so what's in each chest is being read out, and then each inserter is being written to, the specific inserter gets written to here, and then a little bit of extra stuff comes along. You can see there's this green line here that goes off and connects to everything else. So we want to take into account what's in the chests, what we want in the train, how much we want in the train. We have to do this for sort of each one individually. And then we also have to take into account timing, because if there's 2 inserters can pick up at the same time. And so if there's, if this one has 10 and this one has 10, and you want exactly 10, if they both pick up on the same tick before you can sort of detect which one should go first, then it's possible for them both to pick it up and place in. So one cycle of an inserter of picking something up and setting it down between chests, or a chest and the train, is exactly 26 game ticks. And we're going to sort of make use of that. The other thing, timing-wise, that's relevant is that so they're configured as filter inserters. We set the stack size as well. We're going to set it to a specific value, but we'll go into that later. And then we pulse out what's being picked up. The one thing that's very specific and that's unusual in Factorio is that that delay, the delay between when you tell the inserter what it can do and it actually outputting, hey, I just picked up this item, is 2 ticks. Most things in Factorio are 1 tick, or at least all the combinator logic is 1 tick, right? Gets whatever on the input and then writes the output. That's 1 tick. Stack inserters take 2 ticks. So this takes 2 ticks. There are 26 ticks total. And then because there are 12 of them, 12 times 2 is 24. So if we want them to go sequentially, we could put them like a tick apart. But we have at most 2 ticks between one inserter firing and the next one firing. The other thing for that is that when the next inserter is being told what it should pick up, in order to take into account what the previous inserter just picked up, it has to be direct. So what this is outputting, it's going to output, I don't know, I picked up 5 iron plates. The next one over is going to see that output of 5 iron plates because of this green wire, and we have to use that somehow to limit how much the next one should pick up. The one after that, we still have to use what's been like this one has picked up this number, so we have to act on that. But we have 2 ticks between that being signaled and not the next one, but the one after, right? 2 ticks between each. The next one, again, it's on that tick where it actually gets sent out. So this one is going to say tick 0, it's going to get please pick up 5 plates. It's going to pick up the plates somewhere in between and say on tick, not 0, on tick 2, it's going to say I picked up those plates. That's going to be the same tick that this one is deciding what to do. And then those picking up of 5 plates have to apply to like every one after. So for the one immediately after, it's difficult because it has to be like you have to be writing to this and telling it what to do the same tick as you're getting this the output from the previous one. But after that, you have enough time to like do some combinator logic and decide what should be coming back to that one. Yeah. So that's in essence what we're trying to do, right? What should we pick up? How much? We just picked up these things. We want to take that into account. We don't want to pick up too much of something. That's like the key point here. The key thing we're trying not to do. Okay, so that's the goal here. I'm going to switch gears quickly and just talk about what happens when the train arrives. So the only thing hooked up to the train station for now is just the fact that a train exists. So we output the train ID, we're technically outputting the train contents and sending stuff to train, but this is all ignored. The train ID is all that's actually relevant. We read that out. You can see here, we're only checking T. Everything else is going to get blocked. That's the only wire that's connected. And so T is the only thing we care about for now. T, basically, a train exists. We don't actually care which one, so we're just outputting 1 on T because that's easier to deal with. We are going to multiply this by 26. This multiplied by 26 and use that to set up a clock, a 26 tick clock. So this X value is going to fire. It's going to increment every tick. Starts at 0, goes to 25. So from 0 to 25 is 26 ticks. So this is our clock. So basically when the train arrives, start the clock. Every 26 ticks, we are going to have to cycle through all of the inserters and move whatever needs to be moved. And then here we get it. We start getting into the logic. Okay, we have the we have this clock going, 26 ticks. This one goes into what we want to act on. So 2 ticks apart, we want to fire the different inserters. The inserters are each labeled, or their logic is separated into A through L. A, B, C, D, E, F would be the inserters, and I guess they're chests A, B, C, D, E, F, and then G, H, I, J, K, L, right? And 2 ticks apart. So this one fires, and then 2 ticks later, this one fires, 2 ticks fire, this one, 2 ticks later, this one fires, tick, da, 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 etc. So that's what's output from there. So this part, setting up the clock. Okay, so train arrives, start running the clock, start all the logic. Right. Oh, I should mention here, I haven't done any of the logic for the previous chests of should they pass things forward, but I should also point out that I haven't done it. I'm not sure about the logic for the transport belts. In general, this is just stuff comes over from some loading array. Each chest-to-chest connection, or chest to the train connection, is going to have 2 things loading into it, and that's effectively equivalent. The amount of throughput of 2, yeah, I think I might have mentioned that already, works out to be equivalent. Yeah. Okay. Let's go into more itty-bitty details. So, clock starting somewhere here. We'll come back to that later. So, in terms of reading out the value, we're going to look at this particular chest as an example, and the corresponding inserter. So, the chest, the value gets read out, and it goes into this combinator. Now, slight tangent here into what we want to decide based on this. Effectively, what we want to decide, we need to tell this inserter to fire or not. Okay, so it's a filter inserter. Basically, what should it pick up? What should it be willing to pick up? We want to limit that to things that are in the chest, so only things that it could actually pick up. We want to limit that to the amount that we actually want to load into the train, so it doesn't overload the train. So this is relevant for setting the filters, but it's also relevant to the stack size. How many things it's willing to move. The stack size is set on this one by D. Again, remember there are A, B, C, D, so this one is going to be using signal D. And so all these things together sort of have to be coordinated. Again, we'll go into how that works. What else have I said? Oh yes, and then of course reading out of this. It's going to pulse output, and again that happens 2 ticks. So if the 0th tick is hey, we want you to pick something up, it's tick 2, not the next tick, but the tick after that, where it will actually pulse the output. So that's the logic of this, and I point this out specifically and go through it a few times because it will be relevant later. And sort of all these things are specific to how it works. It all has to be just so. Okay. So with the thing of there being one right next to the other, the amount that's picked up, when it pulses and it says, you know, I just picked up 5 plates, right? It's going to output a positive number, a positive 5. and somehow we have to use that to turn, if we've picked up too much, or if it would be too much for the next one to pick up anything, we have to use a positive number to turn off the next inserter. This is possible because of how the numbers are represented in Factorio, in computers in general. All of the circuit numbers are signed 32-bit integers. And I should say signed 32-bit 2's complement integers. So the way this works is that 32 bits is about 4 billion. So you can have 4 billion possible numbers. And what they do is they make half of them negative, right? So if you keep incrementing and you go up past 2 billion something, then it will wrap around and you'll have like a super negative number, right? So adding, subtracting here works. If you subtract all the way to the bottom, you can subtract sort of too much and go around the top. And then if you're at the top and you add a little bit, you can go around to the bottom. So because the filter inserters are, when you're setting filters, if you set a negative number, so 0 or any negative number will turn off the filter. So what we're going to do is, what we're doing here is we use that fact. So when we're trying to turn off the next one, so one fires, and we want to turn off the next one, we're getting a positive output. What we're going to do is set it up so that our limit, rather than being some number, is going to be some negative number down from the top. And so it'll be like add 1, add 2, add 3, add 4, add 5. Flips around to the very bottom and turns it off. And that's sort of the one of the key things that makes it all work. That makes it possible in the first place to do this. So previous one fires, this one we need to take into account again the previous one, all the previous ones, effectively, what's currently in the chest, how much we want in general, and as I mentioned, the last thing was the stack size. And we can also set the stack size, but we also have to set up our logic so it agrees with the stack size, right? If you have a larger stack size, then it isn't safe to load things sooner, right? If this picks up 2 and stack size here is like, well, 10 or 12, and you only wanted a few of something, then it isn't safe to pick it up. So all these things have to be taken into account here at the filter inserter. Well, it has to line up. Okay, setting that part aside. Let's talk about smaller details, and it'll all come together at the end, we hope. All right, so we got steel chests. We have some items in here. Let's just put this one. Let's put a few items in here, and okay, so this has a few items in it. The first combinator simply reduces this to 1. So if something is present, I just want it as a 1. We don't actually care how many there are in it. We just care that there is some available. And the way that we set the size of how many we should pick up is actually based on the total number we want, not the number that are in this chest. So this one's sort of just a signal of I have these things available, and then separately we'll have how much of things we want. We want to filter what we want by what's available, and then once we know what that is, we want to say, okay, how many things should I be picking up? And that's based on the largest of the number of things that we want. Yeah, that'll make sense maybe later, maybe. All right. So basically, if there's anything present, we're getting a 1 out of here, a 1 out of this. You can see it over here. Outputs 1. And then we're outputting 1 billion. Specifically, we're outputting that 1 to the power of 30. So the reason for this, so with a 32-bit number, there are 4 billion possibilities. Half of them are negative. Okay, so we have 2 billion above and 2 billion below, right? 2 billion up to 2 billion something. Technically, it's like 2 to the 30. And then whatever number below 0. Again, so that would be 2 to the 31 above, 2 to the 31 below. 2 billion, 2 billion, 4 billion total. However, for some of our logic, it's helpful to be able to enable or disable thing if only like 2 separate things have to be true at the same time. So for that, because we're what we want to do, we're using like these super large numbers at the top, right? Like we're going to be playing around very close to the top. And so in order to enable this in the first place, what we do is we go condition 1, whatever that is, go negative a billion. Condition 2, whatever that is, go negative another billion. And then our number we're going to deal with of how many things we want to pick up is going to go just like tick, just over, 1 over, 2 over, 3 over, right? So here, this 1 to the power of 30 is going up 1 billion. So we'll worry about making this negative later, but for now we basically have out of all of this 1 billion, right? So we have all that, 1 billion. So that's the reason for having a billion here, and that's what's output. Factorio puts a G at the end, gigahertz, giga iron plates. Yeah. Okay. So that's what's being outputted here. This part here is effectively going to decide what the limit should be. So we're using the value that 1 billion here to turn on particular values of like, hey, whatever amounts I want. I don't have the amount I want set right now, do I? I do not. Let's set that to something so we can talk about it. Let's set that to 10. And right. Don't worry too much about the logic here. This is just to be able to reset this to some amount. I should be using some kind of push buttons, a mod for that, but I ended up doing this on one of my other worlds where I don't want to play with mods, so anyways. So yeah, so that's set to 10. So 10 iron plates, that's what we currently want. And we can see that come across here in the red line. Both the red line and the green line are getting set to that. The red line will get capped at a certain number, like it'll only go so high, but we'll get to that. Okay. So coming across here, coming down the red line, we have that 10. And then coming from here, we have that 2 to the 30, 1 billion. Okay, and that's arriving in these combinators. These are, the purpose of these is to set what D should be, so that A, B, C, D, E, F. The D is the this value is like how many things should we pick up. So we get this value coming in on the red line, which is how many of every item we could have do we want? How many of them do we care about? And because only the ones we actually have in this particular chest are increased by 1 billion, some arbitrary large number, only those ones are going to be relevant to D here. So D is also increased by 1 billion. So basically everything coming into here that we care about gets increased by 1 billion. The things that are in the chest get increased by 1 billion, and D that we care about gets increased by 1 billion. So all the numbers are the same, just everything's shifted up 1 billion. The way these two work is relatively straightforward. So somewhere else, there's a constant combinator constantly trying to put a -1 D. And these just say if there's anything that's greater than or equal to D, then output 1. And also if there's anything that's greater than D, output 1. So both greater, so if there's anything greater than D, or if there's anything greater than or equal to D, output 1. So if D is currently too low, then both of these will get turned on and increase D. Increase the value of D that's on this red wire. That's saved somewhere else. If the value of D is too high, then both of these will turn off, and that -1 that's somewhere else will naturally bring it down. And if D is right where it should be, if D is equal to the one that we have the most of, again filtered by what's in this chest, then D will just stop and stay there. So if it's too low, it gets pulled up. If it's too high, it drops down. This takes a little bit of time to happen, right? Like it will only change by 1 each tick. And so D is constantly riding, I guess generally riding down based on the amount of things we need getting loaded into train. We need less of them. So but it can ride up and down as needed. As more things are required to be put into the train, D will go up, and then as we put things into the train, and it's like, okay, we don't need any more of this item, and now we only have we only want a few of this thing, then D will come down. And so that's done for each of these chest inserter combinations, for A, for B, for C, for D, etc., etc., etc. So each of them independently is riding up and down of how many things should we be inserting into the train, what is the appropriate number that we should be basing further logic, that logic on. The lamps are simply, they flicker when the number changes. That's it, that's all. Yeah, so, and again, everything sort of gets shifted here because we have the really high number, feeds in like that. But the number we get out, so if we look at D here, I can't point at it, but it's like right here. D is 10 here, right? So there's 10 plates, it's set to 10. Oops. And like, that's obviously what we want. But we only have plates here. So if we wanted a whole bunch of, let's say we also wanted 100 100 copper, right? Right. So now I want 10 plates and 100 copper. Two things that are relevant here. First one is that the limit is 12. So again, this is on the red line. Limit is 12, so 12 copper. 10 iron, but D is still 10 because we don't have any of it here, so we don't care what copper is, and that's getting filtered out, right? Only the things we care about are being pushed up that billion, arbitrarily large number, and causing it to affect D here. So that's how that works. That's basically how we're deciding what the stack size should be. We'll go into how it gets written back later, but that's how the stack size is decided. Okay. Here. Dun, 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 dun. What shall we talk about next? Dun, dun, dun. Okay, so D gets decided. I'll run over here quickly and just say, so D and all the other ones are actually getting saved here. So as that increase, decrease on the red line is happening, this is going up and down. We can also see here the negatives that are being applied, again, attached to that red line. And there's the negatives that are being applied, and then Z is being used here to set a lower limit. So we don't ever want the amount we pick up to go below 1. So Z is set to that billion. Remember, everything is shifted over there to make sure that none of the values drop below 1. And we can see that here, D is 10, but everything else by default ends up sitting at 1. So these are all between 1 and 12. And E for us for now is at 10. Another thing I should point out here in this bit of logic, so over here is where we were setting what we want out of the system, okay, and this you can see is sort of coming through this this combinator. It's just a each plus 0 output each, so this is just storing data, right? But you'll notice that the thing that we want, even though it runs through here, doesn't touch this combinator. It's being output here on the red line, and it's obviously over here on the red line. It goes right through that, but doesn't seem to be affecting it. So the way that's done, and this trick is used a few times here, because everything sort of has to be so compact or all the right timing. A lot of things depending on a lot of other things. What we do here is, so first of all, this is how the limit of 12 is set. So this is simply if the value is less than 12, if the value is greater or equal to 12, then either output the number itself or 12, right? And so that's all this is doing, is working out. Should it be 12? Should it be the number itself? And it's computing the negative. So these two on the left are positive, right? Positive 10, positive 12, which are 10 and 12 being the limit. And then this one is the same thing, but negative. So when it gets to this combinator, we just connect up the negatives to it. And it means that this combinator, the positives, the negatives, they're always the same. They cancel out. And so this combinator will never, ever see the value, even though it's passing through it and passing through it on the same line. This is the trick that we're using to get this value onto the red line, even though the red line is also being used for A, B, C, D, F, etc. Yeah. And again, same, you can kind of see the same thing here. Z Z does not go into here, does not get saved here because it's positive here, it's negative here, cancels out, doesn't go out anywhere, right? So it's on the red line, but it doesn't show up in this combinator. So this combinator, may or may not have mentioned, this combinator is the storage, right? The actual information storage for A, B, C, D, E, F, etc. For what they should be, and this is what actually like ticks up, ticks down, and stores that. Yeah, so we have the thing we want, value coming in. This one on the left, and again going out on the red line, is limited. We also have this same value going out again on this green line. In the case of this one, it's not limited, right? So the full 110 are going out. We'll get to why that's relevant later, but basically that's the flow of the information. One, which is we need these things capped to 12, and one which is just we need these things, here's the full total numbers. Yeah, so I think that's the total of, that's the entirety of how A, B, C, D, F, etc. actually get set. And again, they count up and down, and then they'll get used later on. Now let's talk about that part. Okay, so we have the this combinator with A, B, C, D, F, etc. And over here, I talked about earlier, we have the clock coming in. So is the if the train is there, start the clock, and output this one's outputting 1 for A, B, C, D, F, etc. 2 ticks apart. So A, an empty tick, B, an empty tick, C, an empty tick, D, etc. And then at the very end, it doesn't loop immediately. There's technically one that's blank, because, again, an inserter moving is 26 ticks. So we have 12 of them, times 2 is 24. 24 is anyways, there's space for one extra. That one gets skipped at the very end, but we have the clock running. Okay. This number, we're going to do what we've been talking about before, that set of 4 billions trick. So when we actually want to, when the right tick comes along and it's like, okay, it's time for D. We're outputting 1 on D, and it's his turn. What we're going to do to actually trigger that is push down 1 billion. So we want like this negative billion. So this one is effectively sending out negative a billion on A, negative a billion on B, negative a billion on C. Again, it's not exactly negative billion. I think this one's off by 1 to account for something somewhere else. May or may not explain that later. But out of these, it's negative a billion, and that's what this is outputting. And that's sort of what triggers, like, hey, it's time to go, move to the next one. This bit, once again, I am forgetting exactly what this part does. Let's see here. Okay, so this is effectively putting together these values and getting ready to send them out on the right lines. So the number of items to pick up, we have to send to 2 places. We have to send to the part of the logic we haven't talked about yet of telling telling the inserter how much of each item it should pick up, or effectively that if we have this total, that little bit down from the top, like we have to calculate that. So it has to go to there. And then separately, it also has to go to the inserters themselves. And going to the inserters themselves will be like a 1 tick later, because the logic of deciding what things should be put on is going to take 1 tick, because it has to go through one combinator. Effectively, long story short, ABCDF, etc., has to go to 2 places. But the thing that says it's go time (?) also has to yes. The thing saying it's go time does not go to both places, right? So the thing saying it's go time only goes to the logic that says decide what should be moved based on what's available in the chests. Okay. That's effectively what this is doing. It's just breaking up. We're sort of using this trick I described before of we have 2 inputs, make one of them positive, make one of them negative, so that we can not affect a particular combinator, but still get onto the line. So that's happening here. So we can see here that this one, this green line that jumps over here, goes to all the inserters, and we're going to tell it effectively, hey, ABCDF, etc., this is how much stuff you should be picking up. May or may not be able to pick something up right now, but this is how much. And then this one, which is saying it's go time, goes out everywhere else. So again, we're using this sort of double trick again of positive, negative, cancel out. We're doing it here, positive, negative, cancel out. So the ABCDF, this is just for delay, otherwise it would be connected directly. And then we're also going to have to read a value off of this line. This line, this green line down to everything else, is also going to be the line that has the, hey, this, I just picked this up to put it into the train. Like we reduce how much we need now. And so we want to get that out, but we don't want to get the ABCDEF that's being sent in here. So we're basically using that trick to filter out the ABCDEF, and this will only get the amount that was picked up to be put into the train. Only that will make it through this combinator, and that basically comes out over here, as well as being, we can see here, kind of oddly, it gets sent in again, gets sent out on the logic to say what should be written to. And the reason for doing that, I feel like I've gotten a little bit scattered. Let me attempt to summarize what I'm trying to say. When the filter inserter picks up an item, it needs to, it's going to say, hey, I picked up this item. It's gonna pulse. That's going to immediately affect the next one. But for the next one after that, this one needs to be updated with the amount, right? So what's happening here is basically this is getting read out and affects the next one, like immediately. But for the next one, it's going to go out, like it's making its way gradually all the way out to update how much we should pick up, how much we should put in, and update our counter of how much has been put in. And so that's slowly making its way up, but also we have to write it back in for that next one. So again, we read it out, and then we immediately write it back. So you can count the ticks here of this is going to fire. It's going to affect the next one immediately. It's going to go through this, 1 tick, goes over here. This is the logic making its way back, 2 ticks. And then by the time it gets to the next inserter, it's going to have that decrease included in it, right? And so this is negative. This is easier to do as each times -1, but 0 minus each puts a nice negative on it, just so you can see what it's doing a little better. So, long story short, as this is being read out, it's sort of being read out and put back in, and then read out a little bit further being here, and then also being written back in. So it's kind of constantly affecting as it gets further down the logic, until it makes it all the way back to the original decision, the original how much do we need, and just reduces that number. And it's just accounted for, and you don't sort of need this while everything is running, accounting for stuff. Okay. What else here? So, that gets read out. So, 1 tick out, 1 combinator out, 1 combinator back, makes it to the next inserter, and then 2 combinators out, 2 combinators back, makes it to the next inserter. I guess that would be technically the one over here, but they're all on the same line. So, okay. So now what do we have? We've talked about the A, B, C, D, E, F, etc., how they get decided on, how they increase or decrease based on what's available in the chests and how much is needed. And we've worked out what those are, and we've sent them back to the various, like, on these various lines, so we can take advantage of those. Okay, so the last piece that's sort of brings all of this together, and is probably the most complicated piece because it involves all of these, but is the key to the whole thing, is how it gets written back. Let's talk about sort of each piece of that in turn. Okay, so we have a single arithmetic combinator. Okay, and this one is specific to a particular ABCD, etc. So this one is D, but the one next to it would be E, the one next to it would be F, etc. And we're going to subtract everything else from D. This will also actually include D, as opposed to the other case. So D will actually get canceled out here. And so D is not written through this way. And that's why we have to write it on the other line so it comes directly to the inserters. So, okay, D minus each, what does that mean? Okay, so we talked about this sort of, we have the 4 billion, half positive, half negative. We're going to go down, so the things that are writing to this is the 1 billion out of this. However, this is being subtracted, so it's negative. So if we have something available, we're writing out a negative number for it. Okay, so it's negative 1 billion. When it's this guy's turn to fire, we're going to get another negative billion from the clock. Okay, so D will be decreased by another billion. Okay, so now we've reached all the way down to the bottom. And then also on this green line from back at the beginning, If I trace this green line over here, down here, this is also getting written to it the amount we want, the total amount that we want, right? 10, 100, and this is decreased, again, bit by bit as things are being read out. So it's like as up-to-date as you can be for this combinator. So we're subtracting, it's time to go. Let me do it this way. We have this thing available, okay, of each type. Subtracting it's time to go, and we're subtracting its how much of this is available, right? How much more do we want to move, right? And that how much more do we want to move is what's looping us back to the top, right? So now we have this little bit down from the top of how much more do we want to move. So now we have a super positive number saying like that the filter inserter, that the setting filters will be able to detect and say, oh, it's time to move this particular thing. It's not this particular thing. It's time to move. It's time to move this item. It's time to move these specific items. Only the items that we have some of, again, determined by what's coming out of here, and where we actually want that item, and where we're also taking into account the number here will be affected by D of what is the stack size. Okay, so the amount we want needs to be affected by the stack size. So this bit at the top, right? That needs to be affected by the stack size so that we can decide, hey, we've moved enough of this item that if you move the full stack size, it's going to cause a problem. We need to be able to go like, oh, we've only, like, we moved 1 or 2 or moved whatever. Like, if the only thing we're moving is iron and we need a whole bunch of it, we want to be significantly down from the top so that it would take picking up a whole lot of it to turn this inserter off, right? So all of that comes through here, and the final piece of the puzzle of D is included here, the things we actually want to pick up are included here, how much of each one we want is included here, is it time to go is included here, and the last thing, the last sort of calculation that happens is at the filter inserter, we have the last thing not included here is D one more time of what should the stack size be, right? So we get D one more time of what should the stack size be, and the value from the previous inserter, which is firing at that exact moment, is also writing out, you know, are we going to have too much if we move this item? And that will flip it back to the very bottom and set it to false. Yeah, the last thing to point out is this is an each. So if one thing gets flipped around to being false, then something else that is available in this chests can get moved instead. When you get to the end and there's only like a few of like one item you're moving, that might not happen, but sort of that's towards the end of train loading. I hope this last piece made sense of trying to go, you know, have 1 billion, 2 billion, wrap around, and then the last bit of magic happens just because there's two lines connected. D's coming in this way, D's coming in this way. Yeah, and the last thing I should point out is that D is coming this way or this way, and the different values being subtracted. Oops, that's what I wanted. The different values being subtracted either from the previous inserter or from the inserter before that, which has gone out and back, or from the inserter before that, which has gone out and back and back. All of that has to be timed, right? So the value for D that hits this also has to be timed with the value for D that comes in on this line and hits this. So there's one here, right? One there. This one would be 2 and is back to where it's coming from. And then for the other one, it's coming out here. So it's going 1, 2, right? 1, yes, 1, 2, and 1, 2. And that's it. At the very end here, let's do a demonstration. So 5 iron plates here. We're just going to stay with the numbers we've had for now. 110. So we have 5 there. We'll put 6. Let's go. We have 5 there. Put 6 there. Whatever. A bunch here. 5, 11. So it should, like, in theory, it would take 5 and then 5 and then 6 and then 1, or oh, it's 10. 5 and then 4 and then 1. It won't actually do 5 and then 4 and then 1 simply because or do them immediately one after the other, simply because the ABCD is not changing fast enough. So some of these will just be rejected because it's changed quickly. Again, this only happens because it's a number close to 0. I'll put some more. I'll put more copper just sort of around. Just do like that, and you'll see that the copper will it'll just move a whole bunch at once without getting stuck like that. Good enough. All right. Yeah, so again, the amount we want to move, this is reset 110. This is empty. And drives in. And, oh, hello. 10, 14, 8. Interesting. Well, 110. How did it get caught on that one? Maybe we'll have to debug more little things, but in general, it does work. This is probably due to D not being able to go above 12. I could just increase that limit. Do that later. But in general, able to pick up a whole bunch of things. And place into the train. All right. Let's do a larger demonstration of just a number of items. Let's decide what that should be. We'll just do 10 of those. 12. Whoops. 11. 12. 10, 11, 12, and 13. These are difficult numbers because of what the stack size limit is. Technically, my stack size limit might be 8 right now, because I haven't leveled up that much. Anyways. I'm not going to worry about it. Then, there's some iron gears. Just let's do a relatively large number of iron gears. Let's do... What else can I throw in here? Just some inserters. So 50, 25, 13, 12, 11, 10. Now let's say let's take the let's reverse the train before because otherwise it'll just try to put it in immediately. But I want the train to roll up and try to fill. Right. Set up like that. 50, 25, 13, 12, 11, 10. Reset this one as well. Right. I'm just gonna pick some. Do for those. Ta-da. Dun. Be apart. Whole bunch in one. 40. I don't actually have 50, do I? Well. Bring me more. That'll take a minute. Let's continue. What else do we have? Plastic. Yes. Copper, blue inserters. What's it, 25? Yeah, we got enough. Those, bunch of those. Oops. Let's take gears, steel. Some more gears. Up. How many gears we have? 40, 66. Oops. And some steel for there. 3, 4. It's 12, right? And we'll just pick one. That might just load 12 immediately. That's not very exciting. Three, 4. Off by 1 at the very end. Anything else? Da, 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 da. Gears, yes, got him. Plastic nail, da, da. Right. Okay. And once again, it was 50, 25, 13, 12, 11, 10. If 50, 25, 16, 12, 11, 10. 50, 25, 16, 12, 11, 10. Is that the number I just said? 50, 25, 13, 12, 11, 10. 50, 25, 16, 12, 11, 10. Well, we got a bug somewhere. Gotta work that out. Okay, after recording, I went back to see what exactly had happened. So this is after video me now. And it turns out that I had these all set to use D. So control signal D, so it should be D, E, F, G, H, I, J, etc. But all of these are also D. So rather than A, B, C, D, we just had D, 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 E, F, G, H, I, J, K, L. Just check them all. So these should be changed to A, B, C, D. That should be it. I guess we could throw out one more quick demonstration of it actually working. Reset, reset. Let's pick some numbers. Let's do a big number. 301. Just because 1 is going to be a more difficult number. And 15 of these and 40 of these. Keep it simple. 1. Da, 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 da. Control signal. Blah, 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 blah. Oh, and write that out. So 301, 40, 15. If we just put in here 100, 100. Let's put, this one was the one that caused the problem before, looking at the video. So what was it? It was 15 of these. 16 was the problematic number we'd gotten, so let's do that one with 13 again. That's worth resetting. Do the same thing that had caused the problem. 13. Well, same number that caused the problem at least. 301, 40, 13. Let's plug it in here. 100, 100, 100, 100. Would be a good number for these, like 10 apiece. Is it 10, 40? And then I'll just put a bunch here. And in theory, it should just go tuk, 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 and then this one, but again, it might loop around because of deciding that, oh, that number is too high, we can't put that many. Oh, and the stack size right now is 8, so the max stack size is 8. Yeah, that should be it. Good to go. This is empty, yes. Okay, so 301, 40, 13. Three 01, 40, 13. None more needing to be loaded. And from right to left, 301, 40, 13. Thank you very much for watching. It's close. Obviously, still little bits and things here and there. 16. Why'd you move 16? Well, I might leave that for the next person to figure out. Yeah. This is the problem with a giant complicated thing like this. It's like, one little thing went wrong. where do I start to fix it? Just have to reconsider the whole design. But it's most of the way there. It's theoretically possible. It's very close. In general, it works. And yeah. Yeah, that's it. That's all. I think that's been a good time. Thank you very much for watching if you made it all the way through to the end. I think I'm going to do one more demonstration, just have one that doesn't mess up on me. But again, it's important that it's like exact, right? Because otherwise something's going to jam. Like one of these is going to fill up with something, and then everything gets stuck in backlogs, and good luck sorting that out. Has to be right on. Da, da, da. Off, reverse. Something a little simpler. Let's have something work right at the end. Ten, 8, 6, and 50. Oh, and we have to write that out. Ten, 8, 6, 50. Let's go 50, 10, 8, 6. Steel, what was it? Steel, only 6. One, 2, yeah. 1, 2, 3. Steel and some iron. One giant thing of iron. $50, 10, 8, 6. Good, good. Reset. Disconnected. Good. 50, 10, 8, 6. And 50, 10, 8, 6. 50, 10, 8, 6, or 6, 8, 10, 50. It works. Well, didn't work last time, but I'll have to rewatch the video and see if I did something funny, but otherwise, I think that's it. That's all. Thank you so much for watching. Enjoy. Let me know thoughts, and we'll go from here. Thank you very much for your time, and have a wonderful day.